Testing, 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 test, test, test. Testing, 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 test, test, test. Test, 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 test. Okay. Let's see how the stream is going. Okay. So let me figure this out real quick. So what I'm gonna do is I'm writing this book. Let me pull it up actually. Let me just set something up because I've never done this, or I have, but I haven't done this in a while. So let's see how this goes. let's see. The audio should be pretty darn good right now. I think it should be good. Okay, this is the last time. It's just, I'm setting it up. I won't have to do this stuff anymore. I just gotta get it right the first time. Okay, should be good. Hello, hello. Okay, nice. So, what I'm gonna do is, let me switch over. So what I'm gonna do is, I'm reading this book. It's called SICP, second edition. So I'm reading this book. It's called the Wizard book, and this book is really freaking difficult for me. I'm having a hard time on it, I'll be honest. So what I'm thinking is, we'll just spend a lot of time reading this book, going through it, and I'm just gonna do some late night scheme. But I'm trying to see how to capture notes. I kind of want to do org notes because it just looks cool. Oh, it just looks cool, yeah. Let me see. Note taking apps, Windows, Obsidian, OneNote, Evernote, Google Keep, Easy Notes, UpNote, Simple Note, Notes, Joplin. Max. Completely lost on where to start. Install configuration framework. Install Emacs and Doom to get started page. Recommend installing Emacs with Homebrew as it'll make things easier for you in the future. Tutor in the macOS terminal. See, that's just super tedious. Do I want to do that? God, that's terrible. I have Notepad++. Let me use that. I like this app. Sure. So anyways, I'm reading this book. Let me actually get ChatGPT going. So I'm reading this book. It's a classic book, I guess you could say. It's really, it stresses the fundamentals, I guess, and it's a lot of scheme. So what I'm gonna do is I'm just gonna do some late night scheme. Okay, continue. Install that. Agree. Yeah, do whatever you want. Sure. Okay, let's run it. Oh God. I'm gonna make it look like a little notepad. So yeah. me do a new, no, not new. Oh, I just want an empty workspace. I want to close all this garbage. Just want it to be my go-to for what I want. Okay, so I have all this. So to do blah. So what are we thinking? So, okay, I'll use this as my pseudocode writer. I think this will be great for that. But let me first change my preferences. I don't like this look. Looks kind of weird. Yeah, small UI is way better. I kind of like the standard icons. Ugh, those are ugly. Let's see. Okay, dark mode. Just follow windows. Purple, olive, blue. I think I like black, yeah. So basically I'm trying to get good at code, programming. I've been programming for years, but I never locked in the fundamentals. So whenever I scale things up, it's always really complicated for me, which is honestly atrocious. It's like ridiculous that it took this long, but who cares? So, save it on my desktop. I'll just call it, I don't even know how to spell. I'll call it sudo.txt. It'll be my pseudocode thingy. Cool. So let's lock in. Awesome. Okay, so let's open up Scheme. Where is it? So I'm using Dr. Racket. It's pretty much what you're supposed to use for following this book, at least modern. It's pretty solid all around. So sorry I'm doing all this preference stuff. It's just way better for me to get this out of the way now than always be changing it. I'd rather do it now. I guess I like this. Okay. So I got Newton's method going on here. I use vertical. Cool. So basically, I'm on exercise 1.7, so I have this file, and what I want to do with it is I need to find a way to make the good enough function better. So basically I want it to God, I'm so new to all this stuff, all this scheme stuff. It's really like overloading my mind right now. But it's whatever. So we have a function that tests whether things are good enough. So when it tests that things are good enough, what is it doing? Well, it's basically saying, okay, the square root, so x squared minus x, or we'll say guess squared minus x has to be less than some precision threshold value. So that's fine, but we need to absolute this. Basically the absolute value of this has to be less than the precision threshold. And that's fine. So we're defining it here. But the thing is that I'm so iffy about is that I don't know, because what it wants is it says this, it says an alternative strategy for implementing good enough is to watch how guess changes from one iteration to the next and to stop when the changes a very small fraction of the guess. Design a square root procedure that uses this kind of end test. Does this either work better for small and large number? Does this work better for small and large numbers? So I guess what I'm trying to see is, how can I find a way to watch how guess changes from one iteration to the next? So if I wanted to do that, basically, okay, so I want to watch iteration to the next. And then what do I want to do after that? I want to stop when the change is a very small fraction of guess. So the way we do that is basically, okay, let's look at the code. I just have a hard time with it because I'm looking at it and I'm like, okay, if you look at the main function here, you're going in and then you're immediately calling that if statement, which basically you're this if operator or procedure. And what you're saying is you're like, okay, is it good enough? If so, then return the guess value. That is the answer basically. But if it's not good enough, we're going to call the function again with recursion. And if we call the function again, we're going to pass in the improved guess function to improve the guess. And then if we improve the guess, then it'll go back in the function. But what I don't get is that if we wanted to record the guess value from one iteration to the next, so watch how guess changes from one eye to the next, how would we do that? I think, so there's got to be a way I can like record it and then subtract it, because I think what this means is that so I feel like this means, okay, so you have a guess is equals something on the first, and then the guess is equal guess initially, first pass, and then the second pass, guess would be equal to, basically it would be equal to the guess minus the previous guess. The problem is that I'm trying to see how I could do that. And I know my logic is like really flawed right here. I'm not thinking straight, to be honest. But I gotta find a way to make it click in my mind. So what I'm doing is I'm gonna do every single exercise, no matter what. I'm gonna find a way to get them all right. So I don't like these guides. Let me take them out. Okay. So with an improved guess, we take the average of x divided by guess and guess. We average that. So if we wanted to record a guess value here somehow, I think what we would do is we'd say, if the function is not good, and we do this, then something else. Yeah, we'd have to find a way to do both of those things. What I'm trying to see is if the if statement works correctly. Because if statements don't get evaluated in the same way, because they're special cases. So since they're special cases, we gotta treat it differently, basically. And I'm not sure, I'm gonna be honest, I'm not sure how to treat that. So I'm gonna take a guess and I'm gonna say, okay, no, that's not how that works. Maybe instead of the if statement. Thing is, you kind of need an if statement, but maybe I could chain if statements. There's really only one way to tell. So you could go if maybe create a function that records it, that's stored. We don't really need to, because what I could do is define some kind of value. And if I define a value, what would I do? So I define a guess value. So define a guess value, and we'll set it to 1.0 initially. So it's at 1.0. But that's where it starts getting really like iffy about the whole thing with this, because I gotta watch how guess changes from from one iteration to the next. So how would I do that? And here, I guess, I would set guess value to guess. I'm just not sure how, because like the body of the function is not very clear to me how these orders are really defined. Let's see if that still works. Not a procedure. See, how do I set something? I really don't even know how to set something in Scheme. Super complex. Square root. Guess. The new F. Okay. So I guess, okay. What would I be doing? So what I would if a good enough function takes in guess and x values. And the purpose of this function is basically to, I want it to what ultimately is the value that I'm trying to output. I'm trying to find, is it true? Is it true that the new guess is it true that the absolute value of the new guess minus the old guess is greater than, is less than, I'll say 0.01. Is that true? Return that if it's true. That makes it good enough, basically, because that means the new guess, yeah, it's better than the old guess. But I guess what I would do is so that means in this case I'm not really worried about this precision threshold. I'm more worried about, because in this case what I'm saying is okay, is the square root, or no, is guess squared minus x, the absolute value of that, less than the precision threshold, which is the acceptable approximation. But for good enough, basically I would not do that, because I don't care about the approximation threshold really. What would I do instead? Damn, I am not sure. I feel like there's an easy answer here and I'm just like way overcomplicating it. The good enough tests used in the computing square roots will not be very effective for finding the square roots of very small numbers. Also, in real computers, arithmetic operations are almost always performed with limited precision. This makes our test inadequate for very large numbers. Explain these statements with examples showing how the test fails for small and large numbers. Well, first let's show how it fails with small and large numbers, honestly. Let's just do that. Okay, so we got a calculator. Let's see, what did I do? .25024. I mean, it seems fine to me. Yeah, it seems fine. And stop on this. So, okay. So I'll turn for so good enough. So watch. So watch how guess changes. And then stop whenever change very small fraction of the guess. A very small fraction of something, so it'd be, we'll just say 0.1 out of guess. Yeah. I think that works. God, it's so confusing though. Okay. So how could we watch how guess changes though? That's what I don't get. Because I gotta think about how these all fit together. So Okay. I guess we'd create a temp, so it'd be like call it temp, and then we'd store that guess value into it like that. We'd save it. let's see this. So test into X. So I'd want to take, so you have a define tester, I guess. I want to test if you recursed it, if it would keep its value. Maybe I could pass it into one and then store it and then get it back. Because what do they mean by designs? Because maybe... Oh, I see. Yeah. Wow. Man, this is super freaking difficult. I think I just gotta stick with it. Trying to see if this works. You know what? I'll go through YouTube.
And the way you improve the guess is to average the guess and X over the guess. And we'll talk a little bit later about what
This book is humbling, man.
Keep improving the guess until it's good enough. But that's a method. That's how to do something, as opposed to declarative knowledge that says what you're looking for. Like that's a process. Well, what's a process in general? It's kind of hard to say. You can think of it as like a magical spirit that sort of lives in the computer and does something. And the thing that directs the process is a pattern of rules called a procedure. So procedures are the cells, if you like, that control these magical spirits that are the processes. And well, I guess everyone needs a magical language, and sorcerers, right? Real sorcerers use ancient Akkadian or Sumerian or Babylonian or whatever. We're going to conjure our spirits in a magical language called Lisp, which is a language designed for talking about, for casting the spells that are procedures to direct the processes. Now, it's very easy to learn Lisp. In fact, in a few minutes, I'm going to teach you essentially all of Lisp and teach you essentially all of the rules. And you shouldn't find that that particularly surprising. That's sort of like saying it's very easy to learn the rules of chess, and indeed, in a few minutes, you can tell somebody the rules of chess. But of course, that's very different from saying you understand the implications of those rules and how to use those rules to become a masterful chess player. Well, Lisp is the same way. We're going to state the rules in a few minutes, and it'll be very easy to see, but what's really hard is going to be the implications of those rules, right? How you exploit those rules to be a master programmer. And the implications of those rules are going to take us the whole rest of the subject, and of course, way beyond. Okay, so in computer science, we're in the business of formalizing the sort of how-to imperative knowledge, right? How to do stuff. And the real issues of computer science are, of course, not, telling people how to do square roots, because if that was all it was, there would be no big deal. The real problems come when we try to build very, very large systems, right? Computer programs that are thousands of pages long, so long that nobody can really hold them in their heads all at once.
Yeah.
And the only reason that that's possible is because there are techniques for controlling the complexity of these large systems. And these techniques for controlling complexity are what this course is really about. And in some sense, that's really what computer science is about. Now, that may seem like a very strange thing to say, because after all, a lot of people, besides computer scientists, deal with controlling complexity. Right? A large airliner is an extremely complex system, and the aeronautical engineers who design that are dealing with immense complexity. But there's a difference between that kind of complexity and what we deal with in computer science. And that is that computer science, in some sense, isn't real. You see, when an engineer is designing a physical system that's made out of real parts, that the engineers who worry about that have to address problems of tolerance and approximation and noise in the system. So, for example, as an electrical engineer, I can go off and easily build a one-stage amplifier or a two-stage amplifier, and I can imagine cascading a lot of them to build a million-stage amplifier, but it's ridiculous to build such a thing, because long before the millionth stage, the thermal noise in those components way at the beginning is going to get amplified and make the whole thing meaningless. Computer science deals with idealized components. We know as much as we want about these little program and data pieces that we're fitting things together. Right? So we don't have to worry about tolerance, and that means that in building a large program, there's not all that much difference between what I can build and what I can imagine. Because the parts are these abstract entities that I know as much as I want. I know about them as precisely as I'd like. So as opposed to other kinds of engineering where the constraints on what you can build are the constraints of physical systems, the constraints of physics and noise and approximation, the constraints imposed in building large software systems are the limitations of our own minds. So in that sense, computer science is like an abstract form of engineering. It's the kind of engineering
that's how I think about
the
it.
constraints that are imposed by reality.
Okay. Damn, these lectures are better than I thought, even though they're super old.
What are some of these techniques? They're not special to computer science. First technique, which is used in all of engineering, is a kind of abstraction called black box abstraction. Take something and build a box about it. Let's see, for example, you looked at that square root method. I might want to take that and build a box.
Okay, this is the last one I'll get help with. For real this time. So yeah, you taken one. So I was kind of right in a way, but I just didn't know how to set it because I don't know this fucking lambda shit. Like, what the fuck is that? Because with the good enough, yeah, you have guess one and then guess two, but you don't need X anymore. That's bullshit. Yeah, you don't need that anymore. What you do need is some kind of guess one, guess two. I guess I just get super hung up on this shit. So is guess two is the newest guess, so is guess two equal to 0? If it's equal to 0, then either of them needs to be true, basically. If it's equal to 0, returns true. If it's not equal to So if it's basically if guess 2 get minus guess 1, stick the absolute of that though. So if the absolute value of guess 2 minus guess 1, so if delta guess is less than threshold, we'll say so the absolute value of this divided by, see if I show it? Okay. But I don't know why that would happen. So you divide it, so it'd literally just be, so let's see, it would be the absolute value of guess 2 minus guess 1 divided by guess 1. If this is less than 0.001, that's so bizarre. Oh, I guess, so this fraction, this is the fraction of the guess. So if that fraction of the guess is less than that threshold, that precision value, then it's good enough. Oh, okay, I see. S1 is less than okay, so we're good like that. But how do you pass in that guess 1 and guess 2 value? That's what I don't know, because they never discuss the lambda function procedure. They never discuss the set. What the fuck does the lambda do? Creates an anonymous function, a function without a name. It defines a procedure that could take argument and execute. So I guess you just use it within code. Okay, I see. So last time I'm going to do this. Oh, temporary variables. Just create a variable with that name. Okay. Well, shit, I would have liked to know that. I kind of don't like that they don't tell you about those things. I guess it's not a scheme book. So you have to go out and look for those things yourself, I guess. But there's got to be somewhere that gives you a good hint of this stuff. Look at the index. Maybe it has functions or some crap that I could use. Okay. So to create a local variable like this, you'd use let. So you let it get the average stored in here, so you get an improved guess beforehand. Then you check, okay, is the guess and the better guess. It's good enough. If it is, return guess. If not, you're gonna want to send it in with the better guess as the guess, and then throw in the X value. What the hell is that? Shadowing with imports? I'm so confused. I don't know if that's a good thing to be confused this much. Cause like, I don't mind getting confused. I just feel like it's so language specific, like I have no clue. Cause I'm used to just C. It's a lot of stuff that I don't know about. Oh, I see. She said, oh, okay, that's just a way of making it do what we want. And then you set this function so you can create, you can set the squirt define to be lambda You know what? Put that like that. Well, that's not good. So it's a 5e 324. What? Works for 0, even though the guess is always reduced by 50%. this work better for small and large numbers? Well, definitely works for something like 0. Let me put a precision. Because if I put a number that's less than that, then yeah, that's just not accurate, I don't think. 0.0001. 0.01. It's still accurate, but that's only because this works now. 4 it wouldn't work, so definitely works better. Yeah. Yeah, small numbers and large numbers work good. Okay. Exercise 1.8. Newton's method for cube roots is based on the fact that if y is an approximation of the cube root of x, then a better approximation is given by the value. So x divided by y squared plus 2y divided by 3. Use the formula to implement a cube root procedure analogous to the square root procedure. What the fuck does analogous mean? Comparable. Like similar. I shouldn't stress honestly about this because this stuff is really fucking hard. I just gotta try my best. So let's create the new one. We'll call this 1.8. Okay, so with this one though, why does it have Chinese letters? What the fuck? So confused. So I'll call it Cuber, or no, Cuber or Critter. Cuber this. So for this, so y is the approximation or the guess. Okay, so y is the guess. So instead I would say this would be, instead it would be because before the average guesses would be, yeah, you would average it to get a new guess. For this one, so yeah, no, that's fine. Good enough's fine. It's the improved guess that I need to change. So change so we need to divide, so x divided by the square of y. Guess. So x divided by the square of guess. Okay, we have to have, we're adding here. That and multiplication, 2 and guess. All of this divided by 3. Wow. Okay. So all that divided by 3. Let's take a cube root of, oh, what, 64? Oh yeah, critter. Critter this. Oh. Cube root this. Okay, that's pretty accurate. 128. Let's test it. 128. That's not how that works. 5.039. So that's pretty good. Let's test it under that. So it'd be 0.0001. So this is 0.00. Point 0.021545. Okay, that's pretty good. I got this right, but a 1E20. What is 1E20? One times 10 to the 20. Oh, so basically 10. Okay. Yeah. 1E7. Let's see how that is. Point 0.00464. Okay. Jesus, man. Okay. Got it. Finally, I feel good that I got one. Because that 1.7 was nightmare. So square root is our first example of procedure defined by a set of mutually defined procedures. It's the first example of a process defined by a set of mutually defined procedures. Notice that the definition of square rooter is recursive. Yeah. That is, the procedure is defined in terms of itself. Yeah. The idea of being able to define a procedure in terms of itself may be disturbing. It may seem unclear how such a circular definition could make sense at all, much less specify a well-defined process to be carried out by a computer. This will be addressed more carefully in section 1.2, but first let's consider some other important points illustrated by the square example.
Our first step is to download Emacs and its dependencies for Windows. Head on over to www.gnu.org/software/Emacs and click on the Windows button. Then choose to download from the main GNU FTP server. We scroll down to get to the latest. Click on the Windows button. Then choose to download from the main GNU FTP server. We scroll down to get to the latest version of Emacs which is available for download. We need to download 2 of the zip archives. The first is Emacs itself. You need to choose the correct file for your version of Windows. For me, that means downloading the 64-bit. We can just click Windows. For me, that means
Man, I don't need that crap. Much less specify well. Yeah, how such a circular definition can make sense at all. How to tell whether a guess is good enough, how to improve a guess, and so on. How to tell a guess is good, and so on. Okay. Each of these tasks is accomplished by a separate procedure. It's a cluster of procedures. So yeah, the square root problem can be viewed as a cluster of procedures that mirrors the so you're decomposing the problem into subproblems, divide and conquer. It is crucial that each procedure accomplishes an identifiable task that can be used as a module in defining other procedures. For example, when we define the good enough procedure in terms of square, we are able to regard the square procedure as a black box. We're not at that moment concerned with how the procedure computes its result, only with the fact that it computes the square. The details of how the score is computed can be suppressed to be considered at a later time. Indeed, as far as the good enough procedure is concerned, square is not quite a procedure, but rather an abstraction of a procedure, so-called procedural abstraction. This level of abstraction, any procedure that computes the square is equally good. So you have square root problem or procedure that we want to do. We want to be able to take a square root of a number. To do this, we use the square root iter, which basically turns the number into a square root. In order to do that, we need to determine if the guess is good enough. And if it's not, we need to improve the guess. To determine if the guess is good enough, we need to be able to square something and get the absolute value of something. And to improve the guess, we need to be able to take the average. So, divide and conquer. So consider only the values returned. Each takes a numerical argument and produces a square of that number as the value. So you have Okay. If you have function that squares value, what it does is it applies x by itself. That's valid. Or if you had another function that does the same thing. This one's also called square. Takes in an x. I guess these are different ways to go about it. And then the last one is called double, which basically you add it to itself, or you could just multiply it. You add two logs together. So procedure definition should be able to suppress detail. The users of the procedure may not have written the procedure themselves, but may have obtained it from another programmer as a black box. A user should not need to know how the procedure is implemented in order to use it. In order to use it. Okay, fair enough. The implementer's choice of name should not matter to the user of the procedure. For the names for the procedure's formal parameters. Thus, the following procedures should not be distinguishable. Yeah. This principle that the meaning of a procedure should be independent of the parameter names used by its author seems on the surface to be self-evident, but its consequences are profound. The simplest consequence is that the parameter name of a procedure must be local to the body of the procedure. Is that the parameter names of a procedure must be local to the body of the procedure. For example, we use square in the definition of good enough in our square root procedure. Yeah. The intention of the author of good enough is to determine if the square of the first argument is within a given tolerance to the second argument. Yeah. We see that the author of the good enough procedure uses the name guess to refer to the first argument and x to refer to the second argument. The argument of square is guess. Yeah, you pass in guess to that argument. If the author of square used x to refer to the argument, we would see that the x in good enough must be a different x than the one in square. Oh, I see. Running the procedure square must not affect the value of x that is used by good enough. Oh yeah, you can't have it affect it. Because the value of x may be needed by good enough after square is done computing. Yeah, it definitely will be needed. Because this is going to evaluate somehow, and then this is going to evaluate. If the parameters were not local to the bodies of their respective procedures, then the parameter x in square could be confused with the parameter x in good enough. And the behavior of good enough would depend upon which version of square we used. Thus, square would not be the black box we desire. A formal parameter of a procedure has a very special role in the procedure's definition in that it doesn't matter what name the formal parameter has. So yeah, because it has local scope, basically, whenever you actually pass something into it. Such a name is called a bound variable. And we say that the procedure definition binds its formal parameters. The meaning of a procedure definition is unchanged if a bound variable is consistently renamed throughout the definition. Yeah. If a variable, the concept of consistent renaming is actually subtle and difficult to define formally. Famous logicians have made embarrassing errors here. If a variable is not bound, we say that it is free. So, I'm gonna add some text. The meaning of a procedure definition is unchanged if the bound variable. Yeah. If a variable is not bound, we say that it is free. Yeah. The set of expressions for which a binding defines a name is called the scope of that name. For which a binding defines a name is called the scope of that name. So if a variable is procedure definition, I mean a procedure is called so a procedure definition binds its formal parameters. The meaning of a procedure definition is unchanged if a bound variable is consistently renamed throughout the definition. If a variable is not bound, we say that it is free. The set of expressions for which a binding variable a name is called the scope of that name. The set of expressions for which a binding defines a name is called the scope of that name. In a procedure definition, the bound variables declared as the formal parameters of the procedure have the body of the procedure as their scope. Yeah. So if you have a define, and you call it like some function, and you have a formal parameter x, for example, the scope is is the body only, basically. That's their scope, yeah. In the definition of good enough, above guess and X are bound variables, but less than, negative, absolute, and square are free. The meaning of... Yeah, because they belong to that function. They're formal parameters, so they're bound variables. Formal parameters are bound variables. But these other functions, like these procedures, like less than, absolute, negative, square, these are all their own procedures, so they're free. They don't have to depend on good enough. The meaning of good enough should be independent of the names we choose for guess and X, so long as that they are distinct and different from less than, negative, absolute, and square. Yeah, we can't capture that variable. They gotta fit into those spots. As long as you can put them in there, then we're good. It would have changed from free to bound. Yeah. The meaning of good enough is not independent of the names of its free variables. However, wait, what? So it's not. Oh yeah, the free variables definitely do something for it. It surely depends upon the fact, external to this definition, that the symbol's absolute means a procedure for computing. Yeah, it definitely depends on these free variables to do their job. Absolute value of a number, good enough, will compute a different function if we substitute cosine for absolute in this definition, of course. It doesn't do what we set out to do. Yeah, whatever you put in there will fit in there, and they'll have the scope as the body of the procedure. But these free variables can kind of do damage if they don't work correctly. So all the individual parts have to do their job, and they got to do it well. Otherwise, it can fall apart. So the internal definitions and block structures. We have one kind of name isolation available to us thus far. The formal parameters of procedures are local to the body of the procedure. Yeah. Block structures. The square root program illustrates another way in which we would like to control the use of names. Emphasis on control for sure. The existing program consists of separate procedures. You have your square root procedure, you have your square root iter procedure, you have your absolute procedure, your square procedure, your good enough procedure, your improved procedure. The problem with the program is that the only procedure that is important to the users of square root is square root. Yeah. The other procedures, square rooter, iter. Yeah, those can be tucked away and abstracted because those are like under the hood type stuff. Good enough and improve only cloud up their minds. They may not define any other procedure called good enough as part of another program to work together. They may not define any other procedure called good enough. Part of another program to work together with the square root program. Because square root needs it. The problem is especially severe in the construction of large systems by many separate programmers. Yeah. Large systems by many separate programmers. For example, in the construction of a large library of numerical procedures, many numerical functions are computed as successive approximations and thus might, you keep iterating on the approximations until you get better and better results. This might have procedures named good enough and improve as auxiliary procedures. What does auxiliary mean? Supplement. Oh, like assisting procedures. Yeah, these definitely are like helping certain things. We would like to localize the sub procedures, hiding them inside square root. So that square root could coexist with other successive approximations, each having its own private good enough procedure. To make this possible, we allow a procedure to have internal definitions. So we allow a procedure to have internal definitions that are local to that procedure. Yeah. For example, in the square root problem, we can write so we can nest it better basically. So we could say, okay, I want to define square root procedure, have an x value of the square root we want to deal with, and then in this we can define something. We can define a bunch of different auxiliary procedures. So auxiliary procedures are procedures that assist other procedures. Basically like companion procedures. Okay. So with this we have auxiliary, the good enough and then the improve. So define the good enough procedure, which takes in a guess and x. So this checks, okay, is the absolute value. Absolute value is fine. We can have that outside because it could assist these other functions that we care about. So we have something like square function. If you want to square a number, well, you would take that number and multiply by itself. And that's fine because that does what we want it to do, actually. That's pretty great functionality wise. That could do a lot for a lot of different procedures, but in terms of the square root related one, the good enough and the improve the approximation, that's all it has to do with that square root. So you can put it within there, keep it within that local scope. So this is another one, absolute value. If you want absolute value something, just take it. So absolute value something would basically be like, okay, we want to absolute value it. What we do is you would say, so you'd use an if statement. If okay, so if x is less than 0, so if x is less than 0, then no, if x is greater than 0, return x. So basically if it's positive, return x. If it's not, then the alternative would be return negative version of x. Yeah. Cool. Nice. So that absolute should work. So we'd want to take the absolute value of the square root, or the square of the guess. The square of the guess minus x. Take the absolute of that, and we'd want to say, okay, is that, we want it to be less than a certain approximation. So we'll say 0.001. As long as that difference is less than this threshold, then we're good. That's how close we want it to be. That's good enough for that. And then for another define, we'd say, okay, we want another one, auxiliary procedure that improves the guess. Basically, by improving it, what does it do? It takes an average. So if it takes an average, we could use the average function up here, because averages can be done for everything. So we take average, two numbers, x and y. what do we do? Well, we're going to divide by 2, but we're going to divide x plus y divided by 2. That's what we're going to return. That'll be nice. Cool. So to improve, basically improve the guess, what do we do to improve it? Well, we would pass in an average. So we pass in a guess and an x as well. Yeah. And then basically we would return an average of it. So we'd return an average using guess and x. Using x and guess, actually. Nice. And then we would use the square rooter. So we define the square root iter that takes, I guess, an x as well. And then it defines an if statement. So it says, okay, if you do this, then do this. So if the guess is good enough, so if the guess is good enough, and then we'll pass in the guess and the x, then what do we want to do? Well, we could return guess. Else, the alternative would be we would call the square root iter function again, and we would pass in an improved function, an improved value using the guess and the x, which would then average it using that, and then just x. Like that. Then finally what we'd do is we'd be like, okay, basically we got to return some kind of value. So if we want to return some kind of value, pretty sure, well, no, we're good. So we're good with that function, so let's just call it square root. I'll call in the function. Oh, would I call it? Would I call it self? No, right? That seems too good to be true. Maybe I would call it. I'd call it self, and then as the x value in this type of equation. I'd call a square rooter. function. Yeah, which would take in a guess. Start out with a guess of 1, and then whatever x is. Basically. Yeah. Oh, so I define it and then I actually call it. Yeah, my bad. So it's almost there. Just call it. No, let's call it. So square root, if I want the square root of 4. Oh, I wouldn't even need that because I could call it with its local scope. That's pretty nice. So only explicitly. Yeah, we could define these. Yeah, like that. Oh yeah, it doesn't need X. Yeah. Should work now. So this nesting of definitions called block structure is basically the right solution to the simplest name packaging problem. But there's a better idea lurking here. In addition to internalizing the definitions of the auxiliary procedures, we can simplify them. Since x is bound in the definition of square root, the procedure is good enough and proven square rooter, which are defined internally in square root, are in the scope of x, thus it is not necessary to pass x explicitly to each of these procedures. Yeah, so I took all that out. So when you're defining these, you just need to have guess pretty much explicitly used. I'm gonna call it square root this. Square root this. Doesn't do anything. That's strange. in graph. Said we allow x to be a free variable in the internal definitions as shown below. Then x gets its value from the argument from which the enclosing procedure square root is called. This discipline is called lexical scoping. Cool. Lexical scoping. So procedures of a procedure. Okay, so we average. So the average. So we have that average function. It's just averages, which is great. When we're sitting in the average, we send in division. So we send in x divided by guess, and then plus, and what else do we send in? We send in the guess. Okay, there we go. Works. Lexical scoping dictates that free variables and procedures are taken to refer to bindings made by enclosing procedure definitions, that is, they are looked up in the environment in which the procedure was defined. We'll see how this works in detail in Chapter 3 when we study environments and the detailed behavior of the interpreter. We still use block structure extensively to help us. We will use block structure extensively to help us break up larger programs into tractable pieces. So What is tractable? I mean, tractable. Tractable, easy to control. So into easy to control pieces. That's what's important about dealing with large systems, is to be able to manage the sheer chaos of a large system. You have to make it easy to you have to control the flow of data. Into easy to control pieces. Nice, yeah. Let's watch it a little bit.
So it says 2 times the square root of x, and that might be a whole complicated set of rules, and that might end up being a kind of thing where I can put in, say, 36 and say, what's the square root of 36? And out comes 6. Okay? And the important thing is that I'd like to design that so that if George comes along and would like to compute, say, the square root of A plus the square root of B, he can take this thing and use it as a module without having to look inside and build something that looks like this. Like an A and a B, and a square root box, and another square root box, and then something that adds. That would put out the answer. And you can see, just from the fact that I want to do that, is from George's point of view, the internals of what's in here should not be important. So for instance, it shouldn't matter that when I wrote this, I said, I want to find the square root of x. I could have said the square root of y, or the square root of a, or anything at all. Right? That's the fundamental notion of putting something in a box, using black box abstraction to suppress detail. And the reason for that is you want to go off and build bigger boxes.
So we use black box abstraction to suppress detail. To suppress detail.
And the reason for that is you want to go off and build bigger boxes.
So we can build bigger boxes without drowning in detail, basically.
Now there's another reason for doing black box abstraction other than you want to suppress detail for building bigger boxes. Sometimes you want to say that your way of doing something, your how-to method, is an instance of a more general thing. And you'd like your language to be able to express that generality. Let me show you another example, sticking with square root. Let's go back and take another look at that slide with the square root algorithm on it. Right, remember what that says. That says in order to do something, I make a guess, and I improve that guess, and I sort of keep improving that guess. Right, and so there's a general strategy of I'm looking for something, and the way I find it is that I keep improving it. Now that's a particular case of another kind of strategy for finding a fixed point of something. See, a fixed point of a function, is something is a value, fixed point of a function f is a value y such that f of y equals y. And the way I might do that is start with a guess, and if I want something that doesn't change when I keep applying f, I'll keep applying f over and over until
Yeah, if you plug in y, the function equals itself. Fixed point. So start with a guess for y, keep applying f over and over until the result doesn't change very much. Yeah, once it doesn't change very much, find a fixed point of the function y, average of y and x over y.
that result doesn't change very much. Right, so there's a general strategy. And then, for example, to compute the square root of x, I can try and find a fixed point of the function which takes y to the average of x over y. And the idea of that is that if I really had y equal to the square root of x, then y and x over y would be the same value. They'd both be the square root of x, right? Because x over...
So y and x over y would be the same value. Why would that be the case? So x over y. Why would that be the case? Because if you had square root x is equal to y, 2, so y squared. Find a fixed point of the function, so it'd be f of y is equal to y.
Where the square root of x is the square root of x. And so the average, if y were equal to the square root of x, then the average wouldn't change. Right? So the square root of x is a fixed point of that particular function. Now what I'd like to have, I'd like to express the general strategy for finding fixed points. So what I might imagine doing is to be able to use my language to define a box that says fixed point. And just like I could make a box that says square root, and I'd like to be able to express this in my language. Right? So I'd like to express not only the imperative how-to knowledge of a particular thing like square root, but I'd like to be able to express the imperative knowledge of how to do a general thing like how to find fixed points. And in fact, let's go back and look at that slide again. See, not only is this a piece of imperative knowledge, how to find a fixed point, but over here on the bottom, there's another piece of imperative knowledge, which says one way to compute square root is to apply this general fixed point method. So I'd like to also be able to express that imperative knowledge. What would that look like? That would say this fixed point box is such that if I input to it the function that takes y to the average of y and x over y, then what should come out of that fixed point box is a method for finding square roots.
So why would it be x over y? Because if y is the guess and x is what we want square root of, if we took x over y plus x divided that by 2. Why would we do that? Well, we would do that because we'd say how close we got. And then add it to x. But I know, like, with this, what am I doing? I'm doing this something like I'm doing x over y, averaging that with y. Is this supposed to do that though? Because the guess plus the guess. Let me see. Because if you add them and then you divide them by 2, should get you close. I forgot what the formula was. Let's see. So yeah, you're taking plus the guess. So the quotient plus. Yeah. So it's not plus x, it's plus y divided by 2. You're averaging it. That's just Newton's method, basically. The most common way is to use Newton's method of successive approximations, which says that whenever we have a guess y for the value of the square root of a number x, we can perform a simple manipulation to get a better guess by averaging y with x over y. So that's just how you do it. Yeah, it should be like this formula or something. So it's literally it's equal to basically the guess minus however the derivative. There's got to be a non-calculus way to look at it though. Because the same thing is like looking at it like if xn plus 1 is equal to xn minus f of xn over the derivative of it. Well, the derivative at that point Yeah, so x is a guess in this situation. So I would translate this to y n plus 1 is equal to yn minus the value of that function so it's equal to that guess minus I think that's different though, because that tells you what it is. That's a pretty declarative statement, because you're saying x plus sub n plus 1 is equal to x sub n minus f of x sub n over f prime x sub n. That tells you what it's equal to, but it doesn't really tell you how to get that. And that's what he's kind of been talking about.
So in these boxes we're building, we're not only building boxes that you input numbers and output numbers, we're going to be building in boxes that, in effect, compute methods like finding square root. And my take is they're input functions, like y goes to the average of y and x over y. Right? The reason you want to do that, see, the reason this is a procedure, will end up being a procedure, as we'll see, whose value is another procedure. The reason we want to do that is because procedures are going to be our ways of talking about imperative knowledge. And the way to make that very powerful is to be able to talk about other kinds of knowledge. So here is a procedure that, in effect, talks about another procedure. Right? A general strategy that itself talks about general strategies. Okay, well, our first topic in this course, there'll be three major topics, will be black box abstraction. Let's look at that in a little bit more detail. What we're going to do is we'll start out talking about how Lisp is built up out of primitive objects. Right? What does the language supply with us? And we'll see that there are primitive procedures and primitive data. Then we're going to see how do you take those primitives and combine them to make more complicated things. That means of combination. And what we'll see is that there are ways of putting things together, putting primitive procedures together to make more complicated procedures. And we'll see how to put primitive data together to make compound data. Then we'll say, well, having made those compound things, how do you abstract them? How do you put those black boxes around them so you can use them as components in more complex things? And we'll see that's done by defining procedures and a technique for dealing with compound data called data abstraction. And then what's maybe the most important thing is going from just the rules to how does an expert work? How do you express common patterns of doing things, like saying, well, there's a general method of 6-point, and square root is a particular case of that. And we're going to use, our topics will be...
Okay, I'm gonna call it. There's a lot of cool stuff going on. But I will see you later. Till next time.